All right, so let's dive into calculus. At least let's dive into the second part of calculus. So all of you should have taken a class where you've learned about differentiation. I'm going to assume you all know how to differentiate. You know the different rules. You know what derivatives are and everything. So we're going to move on from there. But we're going to look at the second half of calculus. So if you were in my class, I know I definitely talked about this, and I imagine Larry did too when he first introed calculus, or whoever your calc teacher was. But calculus really has two parts. There are two big questions that were trying to be answered that led to the development of calculus, right? And so one of them was finding instantaneous rates of change, finding slopes of tangent lines, finding instantaneous speeds, right? And that's what derivatives did. So you may remember, hopefully, that in Math 105, when we did calculus, you looked at slopes of tangent lines, all slopes of tangent lines, and then you saw all the applications of it, right? You could use them to see when you're increasing and decreasing, and you could use them to find, maxes and mins and all kinds of great stuff. Okay, well, the other question that led to calculus was the area question. All right, so let me just kind of remind you about this. 1 second, you guys. So I can avoid the glare from my light here. But this was the area question, right? The area question was, what if we have some funky shape? How do you find the area? Right? How can you actually find the area of this? Now, there are certain shapes it's really easy to find the area, right? What's the area of a rectangle?
Length times width.
Good, just length times width, right? Base times height, however you want to think about it. All right, so rectangle, easy. How about a circle? You know the area of a circle?
Pi r squared.
Good, pi r squared. You know the radius. You can square it and multiply by pi. Okay, area of a triangle.
1/2 base height.
1/2 base times height. All right, cool. So Suzanne's on it today. I love it. So yeah, certain shapes is really easy. A shape like this, not so much, right? And so this is what actually led to the second half of calculus. This is what led to what we call integral calculus, which is how do we figure out the area of a funky shape like this? Okay, so here was the idea. The idea was, well, what if we approximate this with shapes that we do know, with shapes whose areas we do know, right? So let's use rectangles, circles, triangles, and the like to get the area, or at least to approximate it. All right, now we're going to start with a shape that's not quite as gnarly as this. This one's a little bit more difficult. So let's start with a shape that would be a little bit easier to approximate, but is still not obvious. Still not like, oh yeah, clearly we know what its area is. So what if it was a shape that looked like this? So almost a rectangle, very close to a rectangle, but not quite. Instead of a rectangle, instead of the top being a line segment, it's some sort of funky, weird curve. All right, so here was the idea, and we will refine this and we'll make it work really, really well. But the idea was, okay, instead of just doing this, what if we approximated it with a rectangle? And you just go, well, what if we just did, say, this rectangle right here? If I found the area of that red rectangle, it's going to be pretty close to the area of this weird shape, right? It's not going to be exact, obviously. It's going to be off a little bit, but it'll be close. All right, so that was the idea. Let's just approximate it with a rectangle. Now, mathematicians, of course, realize that better than just one big rectangle was, what if we made a whole bunch of rectangles that were a little bit smaller, but that fit this shape a little bit better? So instead of this red, what if we had a whole series of rectangles that I'm going to make it here in purple? All right, so now I've got, how many? I think I've got 7 rectangles there that are all a little bit smaller. They have variable widths, they have variable heights, whatever. But those 7 definitely approximate the area better, right? It's a better guess than what the one big rectangle was. All right, well, I think you can probably see what's going to happen. How do we make it even a better guess again? Well, make more rectangles. Instead of those 7, what if I have 70? What if I have 500? What if I have 1,000,000? Right? And so the idea was, let's just make it so that we've got more and more and more rectangles, basically letting it go to an infinite number. All right, so this is the approach for integral calculus. The whole idea behind integral calculus is, how do we get this area when it's not a nice shape? And the approach is going to be using rectangles. But before we get there, I want to remind you about something. And this is summation notation, sigma notation. So this is something you saw back in pre-calc. May have been a while ago. So let's make sure we're all up to speed on it, same place. So this is summation notation, sometimes also called sigma notation, because the letter we use to show it is the Greek letter sigma. And that's this guy. So hopefully that looks familiar. Does that look familiar? Remember seeing that before? So how this plays out, this kind of like pointy E, that is the Greek letter sigma. It's the equivalent in Greek of S, our S. That is sigma, it's the capital sigma. But what this tells you is to add. What we're adding are these things. Okay, so I've got here A sub I. This is just really generic. I'm calling the terms A. And so there's a first term, A1. There's a second term, A2. A third term, A3, and so on. Okay, but these are what we're adding up. The I down here, this is called the index. That's often why we use the letter I for it. It's not the square root of -1. Okay, it's not the complex I. It's just a counter. And this tells us where we start and where we end. All right. So in this case, we would start with I equal 1. We end with I equal n. And basically, this is the shorthand of saying we're taking A1 plus A2 plus A3 plus A4 plus ... plus A sub n. All right. So that's also why this is called summation notation, because we're adding stuff up. Okay, summation notation. So hopefully you've seen this. This is really, really generic. So let me give you a specific one, just so that it kind of reminds you how this works. So you might have something like the sum from 2 to 6 of I squared plus 1. All right, so basically what this is saying is that we're going to have our term, like I wrote here, A sub I, it's actually I squared plus 1. We're going to start this at 2, and we're going to keep adding until we get to this one where I is equal to 6. So this would be the same as 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1 plus 6 squared plus 1. So you notice they all have the same form, right? But what we're squaring is going from 2 up to 6. And that's what these starting and ending values are telling us. So we're starting when n is 2, and we're going, or sorry, when I is 2, and we're going all the way until I is equal to 6. All right, well, let's actually get a number. I know you guys are dying to actually have a number here. So this is going to be 5 plus 10 plus 17 plus 26 plus 37. 54, 89, I think that's 95. Y'all can check that for me. But it appears that that is 95. All right, so this is how summation notation works. I'm not going to really go into it further because I'm expecting that you've seen it and you know how it works. But if you're still like me, I don't remember this, come talk to me in office hour, send me an email. Let's definitely chat about it. Because it's going to be really important that we know how to do this when we want to actually do the calculus. All right, so there are some formulas for specific sums that I want to show you. Again, you may have seen these before, you may not. Hopefully you have, but if you haven't, that's okay. I'm not going to prove them. I'm not going to actually prove these statements. Because hopefully you've already seen the proofs. But again, if you're curious, let me know. I'll be more than happy to talk to you about them and prove them to you. All right, so here are just some formulas. Okay. So some things that you definitely should know and be able to use that involve sums. Okay, so the first one is this. What do you get if you add up a constant? So this C is a constant, right? It's like 4, negative 13. Okay, pick your favorite constant. All right, so basically what this is saying is we're taking C and we're adding to it C plus C plus C plus C plus C plus C until we've done it all these times. And it turns out that what we get is actually just C times N. Right? Because repeated addition is the same as multiplication. All right, so we get C times N. Pardon me here, guys. All right. You may have noticed that my other screen disappeared. My computer completely shut down. I'm just glad my phone was still going. So. Anyway, all right. So if you take the same number, just add it up lots of times, that's what multiplication is. So you just get C times N. So an example of this would be, let's say we're doing from 1 to 6 of 4. Okay, well, that would be 4 plus 4 plus 4 plus 4 until we've got 6 of them. Because this is I equals 1, I equals 2, I equals 3, I equals 4, so on, right? First term plus second term plus third term plus fourth term. And so this would end up being just 4 times 6 or 24. So it's actually really easy to get a value for this quickly using this formula. So if you ever have a constant that you're adding repeatedly, you just multiply it by however many you have. But I do want to point out, make sure you realize that this starts at I equals 1. If you start somewhere else, you don't get this number, right? Like if this had been I equals 2 to 6, we actually would have only gotten 20 instead of 24 because there were only 5 terms. So just watch your starting value. But if you start at 1, it's really easy. All right, here's the next one. Is what do you get if you add up i's?
Is it 1?
Well, it starts as 1. Right? Think about what this means. Let me actually write out the first few terms for you. So if we're going to go from 1 to n of I, this is 1 plus 2 plus 3 plus 4 plus all the way out to n. Okay, so what this is actually telling us is just add up the first n integers. All right, now there's a formula for this one. Some of you may remember it, but it's n times n plus 1 over 2. If you don't remember that, that's also okay. But this one, I like to joke about that. This is the one that wins you free root beers at the bar, right? So, because here's how this goes down. You just go, okay, hey, we're gonna have a race to see who can add up numbers fastest. All right. So and you say to the other person, you say you get to pick the other number. So it's not like I've got it memorized. But what we're gonna do is you're gonna say, okay, 37. And we're gonna have a race to see who can go 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus 37 the fastest. This is gonna let you win that root beer every single time. Every single time. Because it's super fast. Right? You want to know what you get when you add 1 plus 2 plus 3 up to 37? Well, it's 37 times 38 divided by 2. And you know, you're probably going, oh, I don't know, that's still a lot. Yeah, that's going to be a lot faster than adding 1 all the way to 37, right? 37 times 38 divided by 2 is 37 times 19, which is going to be 666 plus 37, should be 703, I think, he says with question mark in his voice, right? But you can get to that answer much faster using this formula. Now, this one I am going to show you where it comes from just because I love it and it's got a great story behind it. But this is the fast way of adding numbers 1 to whatever. So like you want to go 1 plus 2 plus 3 all the way to 100. 100 times 101 divided by 2, 5,050. Trust me, way faster than trying to add them individually. Now, where this one comes from is kind of fun. There was a mathematician by the name of Gauss, Carl Friedrich Gauss. He was brilliant. He was one of those like really, really smart kids. You know the ones, right? The ones that everybody wants to punch. Yeah, he was one of those. Even the teachers didn't really like him because he was kind of mouthy. Also kind of a characteristic of the really smart ones. And so when he was little, now this is, I don't know the exact age. I think every time I tell the story, he gets younger. But he was definitely grade school age, 6, 7, 8, something like that. And was basically causing disturbance. And the teacher's like, all right, I got to keep this kid busy. And told him, I want you to add up the numbers 1 through 100. Right? So you can imagine if you've got some little 8-year-old snot-nosed brat who's giving you troubles, you sick them on this problem, it's going to take them a while, right? Okay, well, very shortly, Gauss comes up, it's like, oh, teacher, the answer is 5,050. And the teacher's like, no, you didn't get that fast. Like, show me what you did. And this is what he did. And this is actually true, that he came up with this formula when he was a young child. But this is how he figured it out. He said, well, think about adding the numbers 1 to 100. So we're going to do 1 plus 2 plus 3 plus, there's a whole bunch of other stuff. And then there's a 98 and a 99 and a 100. Now, I'm just going to call this S for right now. He probably didn't call it S. He said, okay, let's just add up the numbers 1 to 100. Now, what we're going to do is the same thing, but reversed. So instead of starting with 1, we're going to start with 100. And then there's a 99 and a 98, and then a whole bunch of other stuff. And then eventually a 3, a 2, and a 1. Okay, so that's also the same value. Well, check this out. If we add these up in columns, 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. I think you're starting to see how this plays out. So each of these things is 101. Well, if you add the same number lots of times, that's the same as multiplying. And there are 100 of those. So you do 100 times 101. But that's actually double what our answer is, right? That's 2 of these things. So what we have to do is divide by 2. And check it out. That's exactly what this formula is when n is 100. It's 100 times 101 divided by 2. All right, so this also shows you kind of the brilliance of this guy. But when he was a child, he figured this out. Figured out this formula. So if you do this generically, if you just do 1 plus 2 plus 3 plus out to n, then all of these things are n plus 1. Add up to n plus 1. You've got n of them. So you have n times n plus 1, and then you got to divide by 2. Anyway, and a little bit ago I said, oh, I'm not going to prove any of these things. And I lied. I'll prove this one because it's fun. All right, so if you have I, just add up the numbers 1 to whatever, 1 to n, that's n times n plus 1 over 2. All right, well, there also are formulas for I squared and I cubed. So let me go ahead and give those to you here as well. So if you were to add up the squares, so 1 plus 4 plus 9 plus 16 plus 25 plus 36, so on. And there's also a formula for that. And it's n times n plus 1 times 2n plus 1 over 6. Definitely not going to prove that one. If you guys remember mathematical induction from pre-calc, this is one that you can prove with induction pretty easily. But there is a formula for the sum of the squares. There's also one for the sum of the cubes. So now what we're going to do, we're going to take 1 plus 8 plus 27 plus 64 plus 125 plus so on and so forth. And I love this one because it's exactly the same as the i's, the 1 plus 2 plus 3. You just square it. It's pretty crazy that it ends up being that. Okay, so again, I don't expect that you remember these. I don't expect that you remember where they came from or anything like that. I expect that you've seen it, all right? But we're going to use it in these. We're going to use these. Okay, so here are some formulas for some powers. There are more for like I to the 4th, I to the 5th, I to the 6th. We're not going to go there. But there are a couple other ones that I want to show you that are going to be important to us. The next one is, what if we have a constant times our terms? So every one of our terms in our sum is c times something. All right, well, I'll actually prove this one to you too, just so you can see where it comes from. So this would be CA1 plus CA2 plus CA3 plus so on down the line, right? So that's what this would look like. But notice that each of those terms has a C in them, which means we can factor it out. So factor it out, you get C times A1 plus A2 plus all the way down here to A sub n. And notice that all that stuff in the brackets is just the sum of the A terms. And so what this rule says is that if you've got a constant multiple in your terms, you can actually factor it out. So I'm going to put a box around it because boxes are the things that you look at to remember. That's what you want to remember. That if every term is a constant multiple, has a constant multiple, you can actually factor that constant out of the sums. That's something you're pretty familiar with. I mean, you can go back to Calc 1, right? Think about what happens when you differentiate with constant multiples. Well, the constant multiple just sticks around. What happens when you anti-differentiate? Constant sticks around. What happens with sums? The constant sticks around. So constant multiples just kind of do that. Okay, so we've got this fact that you can actually factor out a constant. And the I want to address before we actually play is what happens if you have a sum or difference of terms. So we're going to have A plus B, plus or minus. Well, this is another one that if you just think about what's going on, let's say the addition, we have A1 plus B1 plus A2 plus B2 plus A3 plus B3 plus so on and so forth. You can split them apart. Addition lets you move things around, right? So you could get all of the A's together and then all the B's together, which means you can think of this as the sum of the A's plus or minus the sum of the B's. So what this one says is that if you're actually adding or subtracting things, you can do them individually and then add or subtract. And that's actually really similar to what we saw with derivatives, right? With derivatives, have a whole bunch of things being added, then just differentiate each one separately and then add them. It's exactly the same idea. Okay, so I just threw a whole bunch of sum formulas at you. And you're like, oh my God, this quarter of calculus is going to suck. It's not that bad. It really isn't. But what I want to do is show you how we're going to use these. So, for example, let's find the sum from 1 to 10. So we're just going to add the first 10 terms of this. But we're going to find the sum of this polynomial, 3i squared minus 2i plus 1. So these are our terms. Our terms look like 3i squared minus 2i plus 1. But we're going to find the sum of the first 10 of them. All right, so one of our options is just to do brute force. Plug in 1, get a number. Plug in 2, get a number. Plug in 3, get a number. Do that all the way down to 10. And then take those 10 numbers and add them. Right? That is an option of what we can do. And that would work out okay here because we only have 10 numbers. But imagine this was the sum from 1 to 1,000,000. Do you really want to get 1,000,000 numbers and then add those 1,000,000 numbers together? No, right? And mathematicians are all about expedience, right? In my language, I call it we're lazy, right? We try to do as little work as possible. These sum formulas allow us to do this quickly with a little bit of work. All right, so check out how this is going to play out. So first, I've got the addition and subtraction. That tells me I can split this into 3 different sums. There's going to be the sum of 3i squared. Then I'm going to subtract from that the sum of the 2i's. And then I'm going to add to that the sum of the 1's. Okay, so I just used 6. I used rule number 6 here to split this up into 3 sums. Now, rule number 5 lets me do this. That 3 that's in this first one, I can pull that out front. So I have 3 times the sum of the I squareds. I can do the same thing with this 2 on the middle one. I can subtract that out, or pull that out. So I get a -2 times the sum from 1 to 10 of the i's, plus the sum of the 1. So those were rules 5 and 6, just to sort of get us here. But now let's actually evaluate the sums using the formulas. All right, so let's look at the I squared. We've got a formula for that. So that's going to give us 3 times, well, since we're starting at 1, our n is 10. So I'm just going to put 10 into this formula. So I'm going to get 10 times 11 times 21 divided by 6. So look at this one that's up here in black. I'm using exactly this form, but with n equal 10. So 10, 11, 21 divided by 6. Now for the i's, that formula was over here, but that was the one that was n times n plus 1 over 2. So we're going to get 2 times 10 times 11 over 2. And then the 1, I also erased that formula, but that one's going to give us 10 times 1. C times n, the constant times n. All right. Well, now we're ready to just plug and chug and get our numbers. All right. So this 6, it's going to reduce down. It's going to cancel with stuff. And we get 105 times 11, which I believe is 1155. Definitely check my numbers on this. I think that's 1155. This one, the 2's cancel. I get 10 times 11, which is 110. And then I get to add 10 more. And if I did those numbers correctly, which I'm not terribly confident on right now, I get 1055.
You are correct.
Yes. All right. So this 1055 is what we would get if we were to write out those 10 numbers and add them up, right? Like here are those numbers. When I plugged in 1, if I plug in 1, I get 3 minus 2 plus 1, which is 2. When I plug in 2, 12 minus 4 plus 1 is 9. When I plug in 3, 27, 28 minus 6 is 22. Plug in 4, 48 minus 8 is 41. I've only written out the first 4 and I'm already tired of this. When I finally get to the 10th one, I get 300 minus 20 plus 1, which is 281. I think the last one's 281. Right? So not only do I have to calculate out those 10 numbers, then I got to add them all up. I got to that number way faster. And again, if you don't believe me that this is faster, change that from 1 to 10 to from 1 to 100. I'm going to be able to get this answer fast and easy, right? If this was to the first 100 terms, well, this would have been 100 times 101 times 201. This would have been 100 times 101, and this would have been 100 times 1. Done. Really fast. Okay, so this is why all these sum formulas were even shown to you or done, is because it speeds up these summations, right? It speeds up these calculations. Now, everything I just showed you is not calculus, right? None of that is calculus, which makes you start thinking, okay, so why the hell is he showing us all of this? Right? Well, I'm showing it to you because it's necessary to do what we're going to do in calculus, right? That's why I'm showing you in pre-calc. So let's go back to the question at hand, the calculus question, the area question. And let's look at this specific area, right? I want to look at the graph or the shape that's found underneath y equals x squared, but above x equals 0. Okay, so here's y equals x squared, above x equals 0. And specifically, let's look between 0 and 4. Okay, so I want to know this area right there. So it's not really a complicated looking area. I mean, it's almost like it's a triangle, but not quite, right? Because instead of having a line here, we've got a parabola. So it's not the right shape. But this is the area I want to calculate. All right, now, here's what we're going to do. We're going to approximate it with rectangles. We're going to break that shape up into strips, into rectangular strips, to get an approximation for its area. All right, so to do this, we have to start with what's called a partition. And all a partition is, I don't know if you know that word in English, what it means, but like, what is a partition, or what does it mean to partition something in regular language, not in math? Yeah, to separate it, to break it apart, to split it, right? Or yes, it's the window in the limo between the driver and you. I haven't spent a lot of time in a limousine, so I'll have to take your word for it, Adam. But yeah, so partition, when we talk about partitions, it's all about splitting it up, separating, right? It's some sort of idea there, right? But yeah, treating that, we see that when we talk about hard drives and all that, when you partition stuff. So partitioning is all about separating and breaking it up. So in math, when we talk about a partition, if we've got an interval, right? So think about just, we'll look on a real number line, and let's say we're going from A to B. A partition is just splitting this interval up. All right, so for example, I'm going to partition it into, let's say, 5 pieces. All right, so there you go. I just partitioned it into 5 pieces. Here's piece number 1, the red one. Here's piece number 2, black one. Piece number 3, we'll make that light blue. Piece number 4, we'll make orange. And piece number 5 will leave green. But you can see those 5 different pieces, right? This is a partition of that interval. You may be wondering, do all of these widths have to be the same? Because it definitely doesn't look like it on your picture, but for those of you who know me, I'm a horrible artist, so maybe that was my intention. No, for a partition, they can be any kind of length, it doesn't matter. It's just saying I'm splitting it into 5 pieces. That's a partition. Okay, so what we're going to do is we're going to take that interval 0 to 4 and we're going to partition it. We're going to split it up. Now, since we can do it in any kind of way, like if I just said, hey, split this into 4 pieces, every single one of you could come up with a different answer for how to partition it. I bet though, if I said split that into 4 pieces, you all give me the same partition. What partition do you want if we're going to go from 0 to 4, but split it into 4 pieces? Where are you going to split it?
1, 2, 3, 4.
Yeah, you're just going to go, okay, from 0 to 1, 1 to 2, 2 to 3, 3 to 4. Right? You want to do it that way. And that's totally cool. And in fact, that kind of partition, we have a name for that. We call that a regular partition. And regular partition, all this means is that all of the widths are the same. When we do things, we're going to use regular partitions just because it's so much easier if we make it so that all of the widths are the same, if all these things have the same. Okay, so here's what we're going to do. Let's partition this in a regular way. And in this case, let's go with 4 partitions. All right. So we're going to do a regular partition. With 4 intervals. So that just means that we're going to cut it at all of the integers, all the whole numbers. So we can go 0 to 1, 1 to 2, 2 to 3, 3 to 4. Okay, so that's the first step always when you're going to try to do this, is to partition it. How many pieces? They'll tell you in the homework sets, right? And you'll see what we do to make it a better guess. But in this case, it's 4 pieces. I'm going to split it into 4. All right, now here's what we're going to do to approximate this area. We're actually going to make 4 rectangles. Each of those rectangles is going to have width of 1 because it's regular. And to get the heights of these rectangles, we're going to use the endpoints of the intervals. All right, so for example, with this guy right here, let's use the right endpoints. All right, so look at this last one from 3 to 4. The right endpoint is 4, so we're going to run up to the function here at 4 and use that as the height of my rectangle. So the height of the rectangle for that interval, that little subinterval, I'm going to use the right endpoint. I'm going to run up to the function, use that as its height. Okay, so for the one from 2 to 3, we're going to use this rectangle. Notice again, its height came from the right endpoint. From 1 to 2, we're going to use this rectangle, and then from 1 to 0, we're going to use that one. All right, so if we were to do this, we're going to get an approximation for the area. So I'm putting approximately equal to. And this is what it's going to look like. The first one, the first area, well, its width is 1. What's its height for this short one, the one that goes from 0 to 1?
Got 1/2.
It's not 1/2. Think about what I'm doing. I'm using the right interval or the right endpoint. So I'm using 1, and I'm running up to the function. In essence, I'm plugging it into the function. So since this function is x squared, I'm going to square 1, which gives me 1. And I see a bunch of people are putting that in there on the chat. So this one's going to be 1 times 1. All right, the next one has a width of 1, but now its height is going to come from that 2. And when I square 2, I get 4. All right, so what about the third one? How tall is it going to be? It's gonna
9.
be- Yeah, it's going to be 9. We use that 3. We run up to the function. So 3 squared, it's 1 times 9. And then the 4 is 16. So here are the areas of each of those rectangles. Right? They all have a base of 1, but their heights are changing. Their heights are changing by the function. And if I'm using the right endpoints, the heights are 1, 4, 9, and 16. All right, well, so that's 1 plus 4 plus 9 plus 16, which is 30. So what I know is that the area of the shape we're actually looking at, well, that's under x squared, its area is around 30. Now, what do you think? Is 30 a good guess here? Is that a good approximation? So Adam says no. All right, so Adam, I'm going to put you on the spot. Thanks for putting that in the chat. Why do you say no? Why do you think that's not a good approximation?
I mean, as an approximation, yeah, because it's an approximation, but there's all the empty space that you're using. And so that's contributing to the area, and that's not actually part of the area.
Yeah, and I agree with you 100%. Like, look at all of this right here. Right? There's all of that area that we included in this approximation that's not actually part of the real area. Same thing like in this little chunk, right? There's all of this stuff and there's all of that. So there's a lot of area that we included in our estimate that isn't actually there. And in fact, what I know is that the true area is less than this. Right? The actual number is going to be smaller than 30. We've overshot with our guess, right? By using these rectangles, we've definitely overshot our guess of what the actual area is. So is it a good approximation? Is it a bad approximation? I mean, the actual area, by the way, is 21 1/3. So, I mean, how good is 30 compared to 21 1/3? I think most of you would probably say it's not very good, right? And where did that 21 1/3 come from? It's because I know something you don't know yet, but we'll get. All right, so it's a guess, good, bad, I don't know, but it's definitely an overshot. So then what if instead of using right endpoints, we had used the left endpoints? So instead of using the right side to get our heights, what if we'd used the left side? All right, now this is going to change our picture a little bit. I'm going to go to black. Hopefully you can see the difference in your picture here. But if we think about that one from 3 to 4, now instead of using the height from 4, I'm going to use the height from 3. So I'm going to get this black rectangle down here. The 2 to 3, I'm going to run up at 2 and across. That's going to give me this one. The 1 and across gives me this. And then at 0, I actually don't get a rectangle at all. So now, again, all of the widths are 1, but the heights are different. Right? The height of the first one is actually 0 squared, or 0. The second one is 1 squared, then 2 squared, and then 3 squared. So this gives us 0 plus 1 plus 4 plus 9, which is 14. All right, so again, it's an approximation. How good of an approximation?
Wouldn't this be smaller than the actual?
Yep, for sure. Right, so this time we know that the true area is actually bigger than this, because each of those rectangles is actually under counting the curve, the actual area, where before they were over counting. So here's what we know at this point. We know that this actual area is somewhere between 14 and 30. Now, imagine that your boss is like, hey, figure out the area of this. And you come back and say, well, I know it's somewhere between 14 and 30. Your boss is probably not going to be very happy with that approximation, right? Because that's a pretty big swing from 14 to 30. And so you might go, well, what if we just average that halfway in between 14 and 30? That's 22. I don't know if you remember what I told you the actual value is. The actual value is 21 and a third. So that's actually a much better approximation. But clearly, this approximation is not so great. So the question is, what can we do to make it better? So what do you think we could do to this to make it a better guess? All right, so I know you said more integrals. I think maybe you mean more intervals. Yeah, more segments. Yeah, what if we split it into more segments? Would that make it seem better? I mean, even just think about it pictorially, right? I know that picture is now really cluttered, so let me draw another one down here. It's not going to be quite exactly the same, but I'll try to make it as close as I can. And again, we're going out from 0 to 4. All right, let me show you an example where instead of splitting it into 4, like we did before, what if I split it into 8? And again, I'm going to use, I'll just do right endpoints. So what that's going to look like, this has got to be the worst picture I've ever tried drawing of one of these before. Okay, well, we're just going to go with that. All right, I'll get to that question in a second one. All right, so looking at this now, again, we're overshooting. Notice that each of these rectangles is actually bigger area than our true area. But look at how much we're overshooting in each of them. It's less. So this should be a better guess. It'll still be more than the true area, but it's going to be a better guess. If we had done the left endpoint, same thing, it would have been an undercut, but closer to what it actually should have been. Okay, so the question then actually comes, and this was the what Juan Carlos said. He said, how many segments would get significantly close to the actual area? And that actually is the question. How close do we have to get? How many do we need for us to be confident in the area? All right, well, we went from 4 to 8. And you probably would be a lot more comfortable with the number that we get from 8. But what if it was 100? Would you feel pretty confident? I mean, that's a legit question.
I guess, would it depend on what you're measuring?
It could depend on what you're measuring. It could depend on how this function is changing, how big your interval is, and all that. But I definitely like Adam's answer there, where he's like, better. I'd feel better if it was 100, right? Or more confident. Okay, so what if instead of 100 we did 1,000,000? You take that region 0 to 4, split it into, partition it into 1,000,000 intervals that are all equal width. So 0.00004. Would you feel pretty good if you had 1,000,000 of them? Hopefully you're all nodding your heads, because if you had 1,000,000 intervals in that partition, and we did this with a right endpoint, let's say, we'd be really close, right? But the question really is, how close do you want to get? How many do you need? Now, think like a mathematician. What's a mathematician going to say? How many intervals should we have? Maybe you guys don't think like,
As few as possible.
okay, so like never enough. I don't know who that was that just threw that up there, but yeah, actually a mathematician would say, yeah, if you just stop, that's a problem. But then a couple of you put infinity or infinite, right, or infinity, and that's what mathematicians did. They said, okay, well, clearly, if I have more of them, it's a better guess. So what if I just let the number I have go to infinity? So I've got an infinite number of them. Well, we can do that. What tool in calculus lets us have an infinite number in there? What have you seen in calculus that lets us go to an infinite number of them? Yeah, a limit. Thanks, Blake. You remember doing limits? Remember doing infinite limits? The limit as x goes to infinity? Well, what about that? If x is the number of intervals, what if we let x go to infinity? And that's how they got around this area question. They said, let's use areas we know, rectangles. Let's fit these rectangles to the shape. And let's make it so that we've got an infinite number of them. Think about it. As we have more rectangles, their widths get smaller. So we're going to have an infinite number of infinitesimally small things that we're going to add together. Now this is starting to feel a little like calculus. Like think derivatives. There was this idea of infinitely small. We bring those 2 points in our secant line infinitely close to each other so that they look like 1 point, and now it's a tangent line. Well, here's the same idea. We're just going to shrink these subintervals so that they're infinitesimally small, so that we're getting spot on areas. Okay, so this was the whole idea, is we're going to get not just a shit ton of rectangles, we're going to have an infinite number of rectangles. That's going to get us exactly our area. All right, so let's think about what we're doing here with our process, and let's try to make it more generic, except I see we're out of time. So we'll hold off on that until next time. So as always happens, we're already behind schedule. Nothing quite like a math class to be behind schedule on day one. So we're not done with 1.1. We're well into 1.1. So we'll finish it up next time. So we're going to run with this idea. We're going to formalize it. We're going to make it generic. And then we're going to see how those sum formulas that I was talking about earlier help us actually do these calculations. And you'll see how I came up with that number of 21 1/3 as the actual area for this shape. Okay, so for Wednesday, most important thing is to familiarize yourself with Canvas and the syllabus and everything. You can definitely start doing some of the homework from 1.1. You should be able to do quite a few of them. but you're going to run into a point where you haven't seen them, and that we'll take care of on Wednesday. All right. So with that, I'm going to go ahead and stop our recording.